好。OK。对啊。OK。所以好奇，顺便问一下，你们觉得说用中文教跟用英文教差别有很大吗？你觉得我的英文讲的你们听得懂吗？还可以吗？还可以。OK。好。对啊，这个也，如果我的英文讲的有任何问题啊，就是老实讲，有任何问题也跟我讲一声，我可以讲慢一点，或者说讲的用另外一种方法来讲，也都可以哦。OK。好。Anyway, let's continue. Okay. So we already discussed like what the MST is, right? So how do we, design algorithm to deal with this? Okay. First, okay, I want to tell you that, okay, the MST minimum spanning tree, this problem also has what we call the optimal substructure. Say we have an MST tree. Okay. If you remove any edge, okay, from this tree, say this edge is removed. Okay. Then T is partitioned into two subtrees, T1 and T2, right? This is T1, this is T2, obviously, right? Right? Just, MST for any edge, if you remove any edge, it's going to break your tree into two parts. Each part is also a tree, right? Okay? And then, what I'm going to tell you is that subtree T1 is an MST of G1, V1, E1, okay, which is a subgraph of G induced by the vertices of T1. Okay? 也就是说，如果说你把这些的 node 这些节点就是看原来的graph， 你把这些节点跟它相关的那些 edge 把它留下来，跟这些节点的 edge 留下来 ，then 这个 T1 就是就是他们那个subgraph 的 MST。OK。就是这个是那个 V1 E1 的那个定义啦，就是这个 subgraph induced by the vertex T1， 就是 V1 就是这个 T1 嘛，那 E1 就是 XY， 那个 XY 就是在这个 V1 里面的，这个留下来 T1 是它的 MST， 这个也是它的 MST， 那就说是另外一个 subgraph 的 MST， 那 so how do we prove that? Okay, this is actually very easy. Okay, we can prove that by cut and paste. Okay, like well, you guys are, using computer to do the cut and paste all the time, right? So cut and paste can also be used for proof. Okay, how do we do it? Okay, we know like the weight of the tree will be the one that the edge that we remove, plus the weight of T1 and the weight of T2, right? Okay, so that's the weight of our original MST. So if T1 prime, okay, say here, if we are able to find a tree that has even lower total weight for G1, for subgraph G1. Okay, then, okay, let's call that tree T1 prime, okay? So if that's the lower weight spanning tree, then T1, okay? Then T1 prime, okay, T prime, that would be the collection of UV, the edge that we removed, union T1 prime, union T2, okay? This will also be a lower weight spanning tree than T for the whole graph G, right? Because this one stays the same. This one stays the same. The only difference is T1 and the T1 prime, right? And now the T1 prime is claimed to have the lower weight than T1. So obviously the total weight of this tree T prime will have like a smaller total weight, right, than T. But that's a contradiction, right? Because we know T is the T, we claim T is the minimum spanning tree for the graph G. But now you can find another spanning tree with a weight lower than T in the graph G. So that's we have a contradiction here, right? So that's impossible. So this is kind of like this if T1 prime were a lower weight spanning tree than T1, this is we are proved by contradiction. So this is like the assumption we made, and then we can derive the contradiction. So in other words, this assumption is false. Okay, in other words, we will not be able to find a lower weight spanning tree than T1 for G1. So in other words, T1 must be the MST for G1. Okay? So the other part, the T2, the proof of T2 to be like a minimum spanning tree for the graph G2 is similar. Okay, so I will skip that one. Okay, so we have the overlapping subproblem that in the MST here. Okay, as I already told you. Okay, so basically you can, for any spanning tree, minimum spanning tree. Okay, each subset is a minimum spanning tree for a subgraph. Okay, so that's something we know, but unfortunately, this one, okay, the dynamic programming. If we use dynamic programming, that's difficult, okay, because MST exhibit another powerful property. This property, okay, will make it, make it more suitable to use like a greedy algorithm, okay, which leads to the even more efficient algorithm. What is that? Which is a greedy choice property. What is greedy choice property? It's called a locally optimal choice is globally optimal. Okay, what do I mean here? Let T be an MST of G, VE, and let A to be a subset of the vertices, V. Suppose that UV, okay, this H is the least weight H connecting A to V minus A, then this H must be in this tree. I mean, in the MST. It's like this. What I'm talking about is, do we have? This is A. This is V minus A. So we have all the vertices. I mean, now we break the vertices into two sets. One is A, one is V minus A. So of course the union will be the set V, right? So in between these two sets, there must be some edges connecting to these two sets, right? Right? That's what I'm talking about, right? I mean, because this division is arbitrary, so there must be some edges connecting them, and because remember, like the G is connected. If G is not connected, you cannot even have a Riemann spanning tree, right? Okay, so here I'm telling you that, okay, if UV is the least weight edge connecting A to V minus A, so among all these edges, say this edge has the minimum weight, okay, minimum weight among all these edges. Then I'm telling you, this edge must be included in the MST. Okay? So how do we prove that? Okay, how do we prove that? The idea, okay, is like, okay, so so this UV, okay, UV is the least weight edge connecting A to V minus A. So say we divide all the nodes here, okay, into two sets. Like the blue nodes are in A, and the red nodes are in V minus A. Okay. Be very careful. I never say the nodes here are connected or the nodes here are connected. No. I'm not saying that, right? I'm saying the whole graph is connected, right? But the A may not be, just the node A, nodes in A may not be connected. Nodes in V minus A may not be connected. I mean, if you look at here, okay, you can see these nodes obviously are not connected, right? If you only look at V minus A, or if you look at these nodes in V, they are not in A, they are not connected either, right? I mean, if you only consider the nodes in A and their induced graph, induced subgraph, I mean, they are not connected, because like obviously these edges will have to be removed. They will not be in the induced subgraph. Okay, but okay, doesn't matter. Okay, if you break all the vertices into two sets, okay, arbitrary two sets, A and V minus A, and assuming, okay, in between these two sets, okay, this is the least weight edge between these two sets. I'm telling you, okay, there must be, this edge must be connected, must be included in the Riemann spanning tree. How? Consider the unique symbol paths from U to V in T. Okay, we know like in the MST obviously connect all the nodes together, right? MST obviously connects all the nodes together. And also because we know MST is a tree, right? In a tree, okay, if you consider simple path, there's only one path that will lead you from one node to another, right? 如果是一个树的话，如果是一个树，你从一个节点到另外一个节点，如果是一个 simple path， 它就只有一条路，对不对？对不对？你想想看，这个let me repeat. This is supposed to be covered by data structure, but if not, I mean, if you ask me, what is a simple path? Simple path 就是 simple path 的定义就是说，你里面不会有重复的那个节点，也不会有重复的边。OK， 这叫 simple path， 就是从 U 到 V， 当然是中间会有很多可。OK， so from U to V in the minimum spanning tree, okay, T, okay, there must be a simple path from U to V. So this set is like this. Okay, this one. Blah blah blah. Okay, look at here. Okay. And among them, because U is in set A, V is in set V minus A, right? So in this path, there must be an edge that will connect a node in A and a node in V minus A, right? 一定会有在这个 simple path 一定有一个 edge， 它会连接 A 跟 V minus A 的那个节点嘛，对不对 ？For example, in this example, it would be this one, right? 就是这个是 A 嘛，这在 A 里面，这个在 V 减 A 里面，对不对？就是一个是蓝的，一个是红的。就你看这一条，一定会有一个 edge 是从蓝变红嘛，因为这个一个是蓝的，一个是红的。我们这一条路一定会有一个地方，一个 edge， 它会从蓝变红，对不对 ？Okay, so that edge, as I said, I mean it's connecting the nodes in A and the nodes in V minus A, right? So now we can replace this one with this one. Again, cut and paste. Okay, we know this weight, the weight for this edge must be higher than the weight here, right? Because I just tell you that, okay, the UV is the least weight edge connecting A to V minus A, right? So this one is obviously an edge that connecting A to V minus A, right? So these two edges, okay, because they are both like edges connecting A to V minus A. So, and the UV is the smallest, has the smallest weight among all these edges, right? So this one must be cheaper, has a smaller edge than this one, right? So you can cut and paste, get rid of this one and use this one. Just swap UV with the first edge on this path that connect a vertex in A to a vertex in V minus A, which is this one. So you disconnect this one, remove that one from T and use this one. So first, okay, it will still make sure you are still making sure like the whole tree is connected, right? Okay, because like before you use this link, okay, all the nodes are connected, right? It's MST, and now you replace this one with this one. Okay, obviously all the edges, all the nodes are still connected, right? And you have the previous, because it's tree, so you have n minus 1 edges, right? Now you still have n minus 1 edges connecting all the nodes. So it is also a tree. And then, the most important thing, this tree, this spanning tree, has a lower weight than the previous one, right? But that's not possible, right? That's not possible. That's not possible. So a lighter weight spanning tree than T will be created, right? So that's not possible. Because we know like T is supposed to be the MST. So the only explanation is that, okay, this, this UV is already in the tree. Okay. So you cannot like do like a cut and paste. Okay. So there are two famous algorithms out there for MST. Okay, one is the Prim's algorithm, one is the Kruskal algorithm. Okay, we are going to cover Prim's algorithm. For Kruskal algorithm, I would prefer you guys to check it out by yourself. Okay, we don't. This course obviously like is too short to cover like too many algorithms. Okay, so I'm going to cover only like one of them in MST. For the other one, yeah, I'll see what I can do. Okay, so Prim's algorithm, basically, I mean, based on the previous theorem. Based on previous theorem, so if you break the nodes into two sets, the idea is to find the smallest weight among the edges connecting these two sets and include that one into the MST, and then eventually you are going to create MST. So that's like the basic idea. Okay? So you maintain, okay, V minus A as a priority Q. The key in this priority Q will be, the weight of the least weight edge connecting this node to a vertex in A. Okay. Let me skip this one. I will show you the process, and then we'll come back to discuss this. Okay. Okay. I mean, once you understand the process, and then it will be easier for you to understand the algorithm. Otherwise, like it's probably more difficult. We still use the original graph. Okay, and the key. Each node will be placed in the priority queue. Each node will be placed in the priority queue. Okay, the min heap. You guys already know the heap, right? Okay, we talked about heap sort, right? So the heap can be used for the priority queue. Okay, and we assume like the smaller key will be placed in the front. Okay. If you don't forget about heap, like please check like what I covered like in the heap sort. Okay, so basically, okay, so originally, okay, all the nodes will be in V minus A, and there will be no node in A. Okay, there's no node in A, so all the nodes will be in V minus A. So all these nodes are in the priority queue, first. Second, okay, the key, what is the key? The key is like, remember, I'm telling you, the key will be the node in here, okay, to the minimum edge that connecting the node itself to one node in A. But since all nodes are in V minus A, so we assume all the key are infinite. Okay, and of course we need to start from one node, right? So we randomly pick one node. Okay, this random initialization could, it doesn't matter because, why? Because the MST must include all the vertices in there, right? MST include all the vertices. So you could start from any vertex. Here, okay, we start from this node. Okay? So randomly pick this one. And then, okay, in the next iteration, okay, you try to change, because this one is selected into the V, right? Sorry, into the A, right? This node is selected into the A. Then the next iteration, okay, this node, the edges that with the smallest weight that connect it to A will be this one, right? Right? Will be this one, 7, right? And the edge that with the smallest weight that connect this node to A will be this one, right? The edge that connect this one to A with the smallest weight, it will be this one, right? So these three nodes will become, their key will become 7, 10, and 15, right? Right? So you need to update their key. And once you update their key, in the main heap, like once you change their key, you have to adjust that, right? I mean, it's a tree shape, right? So the worst case, I mean, it will be, you'll be going down or going up. You have to adjust that. But so this will be included, okay? And then their key becomes 7, 10, 15, right? 7, 10, 15. And then remember, I mean, we are going to put all these nodes, all these red nodes into the priority queue based on their key, right? So which one will be selected next? 哪一个节点会被下一个会被选？因为我们是 min heap 嘛。那哪一个 key 是最小的？啊，看不出来。应该红色的节点里面哪一个上面的数字最小？7嘛，7嘛，有问题吗？哪一个人会有问题？应该都看得到吧？我的眼睛比你还差哦，我只有一只眼睛，你们有2只眼睛的应该比我好一点，对不对？好，所以你下一个会选这个，对不对 ？You are going to pick this node next, right? Okay. Why? Because remember our theorem. Our theorem tells you that, okay, this one is A, and all the other nodes are V minus A, right? So whichever edge has the smallest weight that connecting V minus A to A would have to be included in the MST, right? So in other words, the theorem guarantees that this edge has to be included, right? Right? So then you are going to include this one into A. So you include this one into A. And then when you change this node, okay, into blue, it's adjacent nodes, its neighbors will have to see if they need to adjust their keys, right? 它的邻居必须要去看看他们是不是需要去调整他们的 key， 对不对 ？So it has 3 neighbors, this neighbor, this neighbor, and this neighbor. So originally they are infinite, but obviously now this key will have to be changed to 9. This key will have to be changed to 12. This key will have to be changed to 5. Right? Right? Okay, so once you made this change, okay, the next round, which edge has to be selected. Or put it another way, which node will be selected?哪一个？就你看红色那些节点，哪一个的值最小？哪一个值最小？是不是这个值最小 ？Right? This one has the smallest value, 5, right? It indicates that, okay, this edge, the edge connecting, its edge connecting to A, okay, is the smallest one among all the edges that connecting between A and V minus A, right? So that's why the next one we need to include this edge into the minimum spanning tree. So, okay, we have that. And then its neighbor, their key needs to be updated. So some nodes may no longer be infinite, but we have to check if their key needs to be reduced. For example, you see, originally this one is 12, right? But obviously now the weight is 6, right? So this 12 has to be updated to become 6. Okay. Similarly, this one originally is 10, but now this one is 8. So this node, its key will have to be updated into 8. And this one obviously will be updated into 14. So we have that, right? And then the next we need to pick like whichever has the smallest key. So which is 6. 6. So we include this edge into a minimum spanning tree. Okay, and then the neighbor is already in the tree. So I mean blue node. So we don't need to do anything. And then we check the which one is has the smallest key, which is 8. So 8 we will include 8. Okay, once you include 8, okay, this neighbor originally is 14. So its key has to be reduced to 3. So it becomes 3. So once you make this update, obviously next one to be added, it will be this node or this edge. This edge. Okay, so you add this edge. And then you add this node and then this node. So the edge that has the edge indicate that that's the edge that is selected. And the direction indicate its parent. Okay? In the minimum spanning tree. Okay? So once you understand the process, let's come back to the algorithm. Okay. Originally, as I said, every node, their key is initialized to be infinite. Okay? To start, it doesn't mean like they will remain that way. Okay? And then we arbitrarily pick a node. Let's say that arbitrary node to be node S. So it make that key to be 0. Okay? That's the beginning. We randomly pick a starting point. As I said, okay, it doesn't matter which node you pick. Okay, but in our example, we pick that particular node. You can try to run the same algorithm from a different beginning node, and see like if it works. Okay, but anyway, okay, we start from node S. While Q is not empty. By the way, all the nodes is inserted in Q, in the priority queue. Okay, all the node is inserted into priority queue. So while Q is not empty, then we get minimum from this node Q. Okay, based on the key. Okay, initially, okay, obviously only node S has a key 0. All the other node has infinite, right? So in the first round, you are going to pick node S, right? You are going to pick node S. And then for each node, for each neighbor of node that you pick, okay, which is S, for each neighbor of S, okay, you do if V, okay, if you check if the value that connecting to this, I mean the S to this node, is going to be smaller than the key or not. If it is smaller, you are going to update the key, and then you are going to do the reheap, basically like maintain a priority queue, okay, and then you are going to assign, okay, because this is like what this is what you pick, okay, you pick U, right? So U, it's going to be V's parent, okay, you assign V's parent to be U, okay, and then, okay, you keep running this one. So so once you understand that, let's come back to the algorithm. Okay, I will go few steps, and then for you to check. So initially, as I say, I initialize from here. So I will get this one from the heap, okay, and then I'm going to update the key of these 3 neighbors, and then I'm going to make this one the parent of these 3 nodes. I mean, this is temporary assignment. Okay. Later on, if you are going to find another node which is better for this parent, it's going to change. Okay. So this is temporary. So next one, as I say, the 7 will be picked. So 7, okay, and then we update these values, and then, okay, we make 7 the parent of these 3 nodes. Okay, and then you can see the next one we're going to pick 5. Okay, so you can see once you pick 5, okay, because this one original its parent is 7, but now because 5, okay, this one, this edge is cheaper than the key, so you are going to make this one key 6. At the same time, you are going to make this 5 the parent of 12 of that node. So it becomes this. Same thing. Okay, originally it's pointing to here, so now it's pointing to there, and so on. So that's it. So I mean, you can check out the rest of the steps by yourself. Okay. So well, I'm running out of time. So let's. So now you understand what Prince algorithm is, but for the analysis, I'm running out of time today. So I think we'll stop for now. Okay. Next time we'll start from the analysis of Prince algorithm. Okay, and then to finish up this lecture. Okay, and also cover something new. Okay. Any question? And remember, I told you first I'm going to upload the programming assignment number 2, and the second the final exam is now on the 11th of the June, and the programming exam is going to be on the 10th of June. Okay, 10th of June, 1 day ahead of a final exam. Okay, that's based on the voting result. Okay， 有人如果说比较晚来的，你有同学比较好心的跟他讲一下，我们前面有投票过，虽然说不是每个人都投票了，但是看起来就是大家的选择还是 prefer 说就第17周就全部都把它解决掉。OK， Then okay.